Jnanam paramam dhyayam. Knowledge is supreme.
Hello students, the topic of this this portion, this presentation is numerator dynamics. So at the end of this lecture, you would be able to compute poles and zeros of any transfer function. You would be able to state the importance of numerator dynamics, which is a part of this lecture, and you will finish by giving you some guidelines about how do you predict step response of any transfer function by computing its poles and zeros. This will be very useful for us going forward when we move to the next module of this process, where we talk about process control. So we will finish the process dynamics portion by giving you the tools which are required to predict response of any general transfer function. So let us get started. So far we have looked at different examples of dynamical systems. We started with the first order processes, second order processes, and then we extended it up to higher order processes. In all those examples, what we considered was all the effect that was coming was from the denominator. So whatever transfer function we had considered, it had some constant in the numerator and some polynomial in S in the denominator. But there are some examples of systems, and especially those are the most of those cases come when we have a controller which is combined with the system. The numerator need not be independent of S. So a general transfer function will be of the form ns over ds, where ns and ds are polynomials in S. So in this lecture we will see what effect does this ns have on the dynamics of this particular system when it is a function of S. So if you recall one example, that was the example when we get a second order system by virtue of having an integral controller on a first order process. In that case, the transfer function which we had gotten for first order process plus integral controller, the transfer function in that case had S in the numerator, and the denominator was the second order transfer function, and the numerator there was S. So this S is going to have a specific effect on this response of this transfer function, which will make it different from how a general Kp over tau square S square plus twice zeta tau S plus 1, this response is much different than when you have S in the numerator. So that is exactly what we will be studying in this particular lecture, that what happens when we have ns which is a function of S. So in order to analyze these kind of systems, we define two terms for a transfer function. So we will write a transfer function as a polynomial representation, ratio of two polynomials ns over ds. So we define poles as roots of the equation ds equal to 0. So you take the denominator polynomial and you equate it to 0, the roots of that give you poles. So those are known as poles of the transfer function, and the poles give the dynamic modes of the process. So by dynamic modes, what I mean is it tells you whether the system is fast or slow, would there be oscillations. So all those dynamic modes which are possible for a system, those would be given by roots of this polynomial ds. And when we have the numerator polynomial as well, then what we get is zeros. So, those are the roots of the numerator polynomial. So, when you take ns and equate it to 0, the roots of that are going to give you what are known as zeros of the transfer function. And poles give you dynamic modes, zeros give you relative contribution of these dynamic modes. So, essentially it will just tell you which of these dynamic modes are dominant, are they moving, all the dynamic modes have same contribution to output or some of them have opposing contribution. So, all that effect will be compressed inside these zeros. And for any typical transfer function, for a what we call as well posed transfer function, which is also like any real transfer function, practically implemented transfer function, what you should have is the numerator degree. So, the degree of the numerator polynomial should be less than equal to the degree of the denominator polynomial. So, that will make it physically realizable. If the numerator degree is greater than the denominator, we will see that those processes are not physically realizable. So, let us try to see the effect of this by using a simple example. So, we will take a second order process with first order numerator dynamics. So, we will take a general form as tau n s plus 1 as the numerator, and in the denominator we will consider two first order series combination, and then depending on the value of tau n we will have different types of numerator dynamics for this particular process. So, we will start with a case and we will look at step response of this particular system. Let us say when we have tau n is equal to 0. So, when tau n is equal to 0, the transfer function is 1 over 2s plus 1 5s plus 1. So, there are no numerator dynamics to speak of, and the response is over damped. So, the response will be something like this. The gain is 1. So, the final value, if the step response or the step change was unity, what you would get is the final value is 1. So, that is what will happen when there is no numerator dynamics. Now, let us consider that tau n is equal to 2. So, when tau n is equal to 2, we are going to have 2n plus 1 and 2n plus 1. So, these two modes would get cancelled, and what you have is 1 over 5s plus 1. So, in fact, this system is going to behave like a first order system with time constant of 5. So, in that case, the response, you can see that the response will be something like this. This is when tau n is equal to 2. So, you can see the stark difference between the original response and this response is that when there was no numerator dynamics, the system was idle for quite some time. So, the response was sigmoidal, which is a characteristic of any higher order overdamped system. But as soon as you have some numerator dynamics, the initial slope is non-zero and the system reacts to the step change immediately. Same thing will be true when I take tau n is equal to 5. In that case, it will be 5s plus 1 over 2s plus 1 5s plus 1. So, these two terms will get cancelled and the response will be 1 over 2s plus 1, which is significantly faster than this. So, in that case, the response will be like this. This is when tau n is equal to 5. So, these are very simpler cases to analyze. Now, the interesting thing will happen when we keep on increasing tau n beyond this 5. So, let us say, or before that let me just redraw some of the responses. When this tau n was, let us say, greater than 0, but between 2, the response would be something like this, which will be faster than tau n equal to 0, but slower than this. So, this is when tau n is equal to 1. When tau n is equal to 3 or 4, the response will be like this. So, what you can see is, as my tau n is increasing from 0, the response is moving in this particular direction. So, what happens if I increase tau n beyond 5? So, the response, what is going to, it is going to push the response in this direction, and the response looks like this. So, you can see that the response is exceeding the ultimate value. There are no oscillations, but the response is exceeding the ultimate value because both the dynamic modes are contributing more than the ultimate value or more than the constant term inside the response, and what you get is overshoot. This is for tau n, let us say, equal to 6, which is greater than 5. So, what we are having is without oscillations or an overdamped system is giving you overshoot. That is possible only when you have numerator dynamics. The other case would be, what if we move in the other direction? So, instead of moving in this direction, we start moving in the other direction and try to reduce tau n below 0. So, let us say if tau n is negative, then the response is going to move in this direction. It has already reached a value where it is almost flat on the x axis. If you increase tau n or decrease tau n further, the response is actually going to go in the opposite direction and then reach the final value. So, what you are seeing is, initially the response is actually going in the opposite direction. So, this type of response you can get when tau n is equal to -1, and this response is known as inverse response. The reason it is called as inverse response is because the final gain between input and output is positive. So, when my input changes by 1 unit, the output is also going to change by 1 unit. But initially, if you look, the change in the input or increase in the input is causing a decrease in the output. So, initial response is exactly opposite to what the final response looks like, and there is a crossing of the response y equal to 0. So, this kind of inverse response happens when also due to numerical dynamics when tau n is negative in this case. So, by just changing what is the numerator, and which is going to change the 0 of the system, the poles of this system remain constant. You can have wide variety of dynamics simply based on the combination of efforts of these two poles. So, by having the contribution change between these dynamic modes, you can have overshoot and you can also have inverse response. So, all that is the product of this numerator transfer function, which is tau n s plus 1. So, by just changing the numerator dynamics, you can have wide variety of possibilities the system can exhibit. We can take another example, this time the first order numerator and first order denominator. And again we can try to find out the response. When tau n is equal to 0, we will have 1 over 5s plus 1. So, the response stays at 0 and then goes to 1 as a first order response. So, this is when tau n is equal to 0. Now, if we increase tau n beyond this value, what you would see is In that case, the response does not start at 0. So, up to time t equal to 0, response is 0, and suddenly the response starts at some value non-zero and then goes to this final value as a first order response. So, let us say this is tau n is equal to 1. So, there is a discontinuity at t equal to 0. You can find this initial value by using initial value theorem. So, this discontinuity will keep on increasing as you increase tau n. When tau n is equal to 5, what you are going to get is 5s plus 1 over 5s plus 1. So, the transfer function becomes unity. That means, it is an instantaneous process with gain 1. So, the input and output are exactly identical. So, input was a step, so output will also be a step. So, what you will get is a discontinuity of value 1. So, output will also be a step, unit step response or unit step. So, we have been increasing tau n and the response is moving in this direction. As tau n goes beyond 5, in that case what you would see is the response will start at value higher than 1 and it will go down to 1. So, again what you are going to have is an overshoot when tau n is greater than 5. And similarly, by the extension like the previous example, if we move in the opposite direction and tau n is negative, the value will actually start below 0 and then it will go up to the value of 1. So, you will have, when tau n is less than 0, you will have inverse response. So, again having the same dynamic mode, which is 5s plus 1 over 5s plus 1, by changing the numerator transfer function you get overshoot, some discontinuity in the input at time t equal to 0 and then the inverse response as well. Now, this type of transfer function is also known as a lead lag type of transfer function. Because the degree of numerator is equal to the degree of denominator. So, denominator is a first order lag and numerator is a first order lead. So, this type of transfer function is known as a lead lag type of system. When we analyze control systems, we will see that some of the transfer functions which we get which will be of this form. So, depending on the value of tau n, we may have some kind of overshoot or inverse response. So, we have seen that by having some polynomial in the numerator, we can get different types of dynamics which were not possible when we had a constant in the numerator. Specifically, we can get overshoot even for non-oscillatory behavior, and we can get something which is known as inverse response, which is one of the difficult or the most difficult type of dynamics to control in any chemical processes. So, we will try to analyze this inverse response a little bit further about why it happens or how it happens. So, inverse response is a type of response when the initial direction of output is different than the final direction of output change. So, initially the output goes in the negative direction, but the final gain or the final direction is positive. So, having such kind of a response is known as the inverse response, when the system initially shows exactly opposite direction of movement as compared to the final direction of movement, which is an increase in the output, but initially you can see that there was a decrease in the output. Now, these type of processes are extremely difficult to control. because what's going to happen is as soon as the controller makes a move. So, let us say in this case the controller has to move the output from this point to this point, and this will happen if he makes a positive move or positive step change in the input. So, now what is going to happen is whenever the controller makes a positive step in the input, initially the output is going to deviate or show. So, initially output is going to move in the opposite direction. So, the controller is going to think that it has made an exactly wrong move or exactly opposite move. So, the controller is going to make a reverse move in that case, which is wrong, because for this particular system the correct input is an increase in the input, but if the controller makes a opposite move, it is not going to be able to get this particular type of response. The response it is going to lead the system to is the mirror image of this, and the system will never be able to reach this particular point, it will go in the opposite direction. So, what happens is every time the system the controller will try to make an exactly opposite move, and the system will either end up at this point or it will keep on oscillating between the operating points, and the system will never be able to reach this particular final output point. Because of that, the inverse responses are very difficult to control, and we should know when we get inverse responses. It is always better to know that the system exhibits inverse response, then some corrective action can be taken or has to be taken in order to control that process. So, let us look more into when do we get inverse response. That is, what is the physics of the process? What is the physics of the process which will give you inverse response? So, as it turns out, inverse responses happen because there are two competing effects which are triggered by the input. So, if this is my input, when I change my input, it is going to change the output in two ways. So, there are two parallel processes which take place, and the net output is the combination of the two. So, there are two parallel processes which are taking place, and as it turns out they have to follow certain rules, then only you will get inverse response. So, let us say G1 is which has positive gain. So, this Y1 increases when U increases, but it is slower, as against G2 which has negative gain. So, that means when U increases, Y2 in fact decreases, but it is a faster response. So, you need to have two transfer functions between the input and output which are in parallel with each other. The one effect has a positive gain and slower, and the other has negative gain and faster. The same thing, this can also be negative, in that case this has to be positive. So, the idea is there are two parallel processes which are operating at different time scales, and the gains are opposite to each other. The gain being opposite is very essential, and they also have different time scales. So, when you have that, under certain conditions or values of these different gains as well as time constants, you will get the inverse response, and mathematically you can find that out. So, any physical system which is going to give you inverse response is going to have these kind of parallel processes which are happening. So, if I want to give you some literature examples, the very common system which gives inverse response is boiler a drum boiler level as a response to change in cold feed water. So, if you have a boiler, this is the outlet for steam, and typically you want to control this level by changing the feed water. So, as it turns out, when you increase the feed water flow rate, ideally what you expect is that the level should increase because you are adding more material into the process. However, what happens is whenever you have such kind of a system, when you are boiling this liquid, there will also be some bubbles of this steam which are inside the liquid, and the height is actually the addition of actual liquid height plus the rise in the height because of these bubbles. When you add cold feed water in, then the volume of these droplets go down, and as the volume of these droplets go down, the actual level goes down. So, the response of the level looks something like this as a response to step change in the input, and you get inverse response. It is a very commonly studied process where you get inverse response. The other system which can give you inverse response is the reboiler part level or even composition in distillation column. As a response to reboiler duty. So, what happens is, let us say if you take the bottom of the distillation column, let us say this is the nth tray, and then this is your reboiler where you provide heat. What is going to happen is, when you increase the reboiler duty, the amount of vapor which goes up into the column increases, and as this vapor increases, it causes puts a force on this liquid which is on nth tray, and it pushes more liquid down. So, the amount of vapor increase in this case is countered by more liquid which falls down, and even though we are boiling more liquid inside this reboiler, the net hold up of the reboiler momentarily increases. So, even though you increase the reboiler duty, the level inside the reboiler keeps on increases momentarily before it starts to reduce. And same way the composition, as you are mixing some low composition liquid into the reboiler, because of this effect the purity also goes down. So, ideally what you expect is when the reboiler duty increases, the reboiler level you want to go down, but initially you see that the level increases and then the level goes down, and the opposite effect is on the composition. So, if you look at the composition of less volatile, as you increase the reboiler duty you want it to be purer, but what you see is initially the purity goes down, that is because of the mixing of this low quality liquid into the reboiler, and then eventually it goes to a higher value. So, in both these cases you get inverse response. So, we'll stop here for this lecture. Thank you.